VLSos here. This is a video lesson on volume by cross-section. This technique can create and find the volume of a vast number of different solids. And this technique does not use the idea of spinning or revolving around an axis. I've started an example problem to introduce the strategy. Find the volume of the solid whose base is the area under a function f, which is equal to e to the x, on the interval from 1 to 4, and whose cross-sections are rectangles with base parallel to the y-axis and height twice the base, which is a lot to take in. Our strategy is to visualize, diagram, and graph before attempting to make the integral to calculate the volume. And the first thing to do is to graph the function given, which is e to the x. I have a graph of that exponential curve, and we're told that the area under this curve on the interval from 1 to 4, which is shaded in, is going to be the base of a solid. So we could imagine a solid resting on our paper, and if it did, where it contacted the paper, the base that the solid was resting on would be that region with that shape. But how is the rest of the solid created, and what does it look like? Let's make sense of the second half of these words. It says, whose cross-sections, so the solid's cross-sections, or what we would get if we sliced the solid and then looked at the shape of those slices. Those cross-sections are rectangles. And what do we know about that rectangular cross-section? They have a base parallel to the y-axis. Now we're thinking about a rectangle, which is a two-dimensional shape. So the base of a two-dimensional shape is going to be a line, and those lines are parallel to the y-axis. The y-axis, or the vertical axis, is right there. And what else do we know about the rectangle? It has a height twice the rectangle's base. Okay, let's put that all together and try to visualize it. Well, if we have a solid that would be resting on our paper so that this would be the base of that solid, then slicing it would mean creating a slice that was rectangular in shape, and the base of that rectangle would be a line parallel to the y-axis, which means that function values can create bases of rectangles. The height of each rectangle is going to be twice the measure of this base. So if I could visualize, I would have a rectangle standing off of my paper that would, at any point along the function, have a different height, because the height of the rectangle would be double the function value that I was using for the base. And the function values change, therefore the heights of those rectangles are going to change. Now I'm going to draw a representative slice. These are the shapes that I'm adding together to create the solid. I create a rectangular slice with the value of the function here. I create rectangular slices for every value in between, and then the last rectangular slice is created by the last function value at 4. Every time I'm going to be adding up the area of a rectangle. And the area of a rectangle is base times height. But we know something from the wording of the problem about the relationship of height and base. The height is always twice the base. So the area of this rectangle is going to be the base of the rectangle, which I've labeled B, times the height, which is twice that B value, which means that if I multiply these, then the area is going to be 2 times its base squared. So what's the base of the rectangle? The base comes from function values. This function is e to the x. So something else that can be said is the base of every rectangle comes from or is equal to the function e to the x, which helps me to modify my area problem or my area expression to be 2 times e to the x and then squared. With a power property, I can bring the power of a power together and simplify it to 2e to the 2x. Okay, maybe if we could visualize this solid in 3 dimensions on our paper, we might have more confidence that this geometry and this expression to add up rectangle areas is working for us. So to do that, I'm going to consider this shaded region as the base of a solid. I need to visualize this region in perspective to be able to attempt a 3-dimensional drawing on my paper. So I'm going to take this region and I'm going to visualize it as if it was tilted in perspective and attempt to draw that. It would look something like this. Where this line corresponds to the beginning value at 1, and this line corresponding to the ending value at 4, this is the base of a solid. And the representative slice line here could be visualized like this. Now we're going to create cross sections that are rectangular in shape. So when we do, the rectangle that gets created ought to have a height that is twice the base measure. So if this line has that measure for its base, a rectangle that comes off of it might look like this, higher than it is wide. The rectangle that comes off here is going to be much higher and go into the wording of my problem. And the rectangular slice in this representation is going to be between the 2 end slices, or the 2 rectangles. So as the function values increase, the heights of the rectangles increase. And if we then attach the contours to show all of the rectangles in between, we've created the illusion of a solid that looks like a flaring up statue. We might call this paperweight. Okay, this representative slice represents any rectangle, and if we're going to create the solid, we need to sum up an infinite number of infinitely thin rectangles with an integral. So the volume of this solid is going to be the sum, or the integral, of all the rectangles that get created with the area formula for these rectangles 2e to the 2x with respects to x. The first rectangle that gets created is at an x value of 1, and the last rectangle that gets created has an x value of 4, so we have the bounds of integration. After this, it's a process of evaluating a definite integral. The integrand here is fairly simplistic. We have the constant 2 times the composite function e to the 2x. E to the x is its own integral, so e to the 2x is going to be e to the 2x divided by the derivative of 2x, which is 2. And if we're dividing by 2, it'll cancel the multiplication by 2. So the antiderivative of 2 to the e to the 2x is e to the 2x. And with the fundamental theorem of calculus, we'll need to evaluate that antiderivative from 1 to 4. So we have the expression e to the 8th minus e squared. These terms are not like, but they can be evaluated. This is the simplest way to express the exact value. We can use a calculator to approximate it if we needed to in the end.